Okay, hi everyone. My name is Mohammed. I'm a master student at the Biomedical Informatics Department at Harvard. This is my email if anyone wants to ask any questions about this. But today we'll be talking about the 3D baseline for this task. So basically, to get to it, so the 3D baseline has the 3D task has two separate tasks. One is medical report generation, and the other is VQA, visual question answering. For medical report generation, we do it region specific, so we don't evaluate the entire report because we noticed that a long CT report, when you pass in a long CT report to green, the performance can be degraded. So we use it per region. So we split the report into different regions, and then we evaluate each region in isolation, and then we average the performance. And then for visual question answering, there's two types. There's a global and local VQA. The global VQA just basically asks about all of the conditions that are present in the scan, and then we give around 40 different options. The local VQA is chain-based questions, so we ask one specific question based on a finding, and then multiple follow-up questions. And you will see what that looks like in the upcoming slides. But for the dataset, so this task is split into two datasets. One is AMOS, and the other is a subset of CT rate. For AMOS, there's around 1,200 examples. There's 12,000 local VQA questions, and then this covers the abdomen region. CT rate covers the chest region, and there's 2,000 examples. The number of global VQA questions is identical to the number of training examples. So each training example, we ask one global, and then there can be multiple local VQAs. So this is an example, a quick example of what the report looks like. So you can see it's split into different regions. And then we evaluate each region in isolation. This is what the global VQA looks like. It's all the same question for each example. It's all the same question for each example, but different. CT rate is different than AMOS because CT rate looks at chest, AMOS looks at abdomen. But basically just asks which of the following conditions are present, and then it gives you multiple choices. The model should generate an answer like this of the multiple conditions that are in there. Okay, this is more complicated. The local VQA. So what does this look like? So we ask one question, which we call the main or root question. This question is basically just a binary yes or no. So it says, is there a thickened appendix with surrounding fat stranding? So this can have either have a yes or no answer, but based on it, there can be multiple, like 2 to 4 follow-up questions. So this one, for example, says, what's the most likely clinical application of these findings? And you have the answer here. So this is a follow-up to question 1, and then there can be multiple follow-ups to question 1. One thing to note here is that the most important question is the main question. If you answer this one wrong, then the entire chain would be considered wrong in the calculation of the final accuracy in this. And I'll talk more about the actual calculation of that in the upcoming slides. So for report generation, we use green, like I said. We use region-wise green. And then one important thing to note, is that if a region is mentioned in the ground truth but not in the generated report that you provided, the green score will be 0. But if it's the opposite, if a region is in the generated report but not in the ground truth, then we compare it to just a normal ground truth for that region. So we just assume that's normal. We pass in that this region is normal, and your prediction is compared against that. For VQA evaluation, we use accuracy. So for global VQA, we just take the union set over the cardinality of the max. So if your model makes 10 predictions, only 3 are correct, you're going to get 30%. For local VQA, like I said, it depends on the root question. So if you get the root question incorrect, you're always going to get 0. Otherwise, you're going to get the proportion of answers that you got correct. So if there's 3 questions in this chain, you get 2, you're going to get 67%.
But otherwise, if you get the root incorrect, then it's going to be 0, and then the accuracy is calculated by averaging the chain, the accuracies across all chains. So let's talk about model development. So I want to highlight one of our recent MICAI papers. You can use this to build on the baseline that we showed here. Basically, we showed that freezing the LLM actually surprisingly performs better than using LoRa or fully fine-tuning it. We showed that if you include the segmentation mask, so if you use total segmenter, extract the segmentation masks of different organs and pass that along with the CT, you can have a better performance than just using the CT volume. And then we also show some additional, we call them report augmentation techniques, ways to improve the final report by one thing you can do is train an additional model that just answers specific questions about some common findings with a yes or no answer. And depending on the answer, you can augment the report with an additional finding. So we check if a finding is already on the report. If it's not, then you ask a question. You ask this additional model question about it. If it answers yes, then you add this finding. If no, then you add a normality about this finding. You can do some like additional augmentation-based techniques like that. And you can also like do naively just add a normal. If an organ is not mentioned or a region is not mentioned, you can just add that it's normal, and this should improve your green square balance. So this is one of the tables from our paper. You can see here. One thing we also showed is that the performance of the LLM itself is not that variable. The projector does matter a lot, which projector you use. So we showed that M3D projector is better than, for 3D is better than using just a naive MLP or a token projector. And then the fine-tuning method, we showed that freezing the LLM actually performs better than using parameter-efficient fine-tuning or fully fine-tuning. And then this is the report augmentation methods that I talked about. You can learn more about them in the paper once it's public. It's going to be public within the next 2 days, hopefully. You can take a look at what we did here, and you can try to do something similar if you want. So for the computation baseline, we used Phi3. Trained it for 75 epochs on both. One important thing to note here is that the model should be trained on both tasks, just one model for both tasks. We used the M3D projector, 75 epochs. We used this volume size because this is the volume size that the M3D VAT was pre-trained on. MedGemma was released very recently. One hidden tip is you can try evaluating MedGemma for this, because all of the, except from M3D Phi3, all of the other LLMs we evaluated were natural LLMs. They're not medical ones. So this might be slightly better. You can try. So what results should you expect from this baseline? These are the results here. So for the VQA, you should see around 60% accuracy, 59 specifically on the local VQA. 0.17 for the global. Global one is a much harder task because you have so many different options to evaluate from. And then green, for these different regions, you should expect something like this. For the breast tissue and diaphragm, there's only little examples. So you could try doing some sort of weighted training here if you want to improve performance on these. Also for the VQA, one suggestion I might have is since the root question is the more important one, you could also weight it more in your training than the other questions. Weight it more in the loss. Okay, so let's get started. So let's set up the code and environment needed. So these versions are very important. If you go above 3.12 here, it's going to break. The code is going to break. So it's important to follow these versions. We're going to do the data pre-processing or look at the code for doing that, and then training and then inference. So let's get started. So so first thing, you have to make a virtual environment and then install all of the packages. So to do that, you just use this command. This will start a virtual environment for Python 3.11. So I can do that here. and then you go into the virtual environment. And then next you have to clone the GitHub repo, this repo where we also explain these steps and provide the code that we used for getting the baseline. So let's clone the GitHub. Let's go inside, and then let's install the requirements. Okay, so while this is installing, the next step is to clone the dataset repo. So the dataset lives in Hugging Face in this repository. Use this command to clone it, and the repository has this structure. So it's split into train and validation, and then AMOS and CT-rate are in different folders. And then we have two JSONs, one for AMOS and then one for CT-rate. For validation, it's just a single folder, images, and then single JSON, a val JSON here for this. And what does it actually look like? So if we just open it up, you can see this is the AMOS JSON. So it has the case ID, the different findings here split into different regions, like I said. Also provide the impressions, and then global VQA. So this is the same question asked on all examples. So which of the following conditions are present in the scan? Select or apply, leave empty if none, and then I give you all these huge number of choices to select from. Then these are the answers. So this is the global, and then the local VQA is a bit more complicated to understand, but basically you have this local VQA key here, and then you go inside. There's an ID. If the follow-up is -1, this means this is a root or main question. So we can see the answer here is either yes or no. And then if the follow-up is not -1, this means that this is a chained question based on the ID here. So this is chained on this ID1. This is also chained on this. So this is a follow-up to this initial question. And you can see here, and then so this is one chain. Here, all three questions here are on one chain, and then the two questions here are another independent chain. It's still installing, but once you clone the repo, you will have this type of structure, folder structure. Once that's done, you can pre-process the data. I'm not going to do that now, but this is the command to do it. You basically pass in the JSON, you pass in the folder for the data they will pre-process. You pass in the output directory and then number 4. Because one important thing to note here is that you should do it for all three sets. So we do it for AMOS, CT-rate, and then the validation. So you just pass in the AMOS JSON folder, the nifty directory for the CT-rate, and then the nifty directory for the CT-rate, and then the output directory where the pre-processed volumes are going to be stored. So inside the data preparation script, what this does is basically it does windowing based on if the file is AMOS or CT-rate. So if it's a chest or abdomen CT, and then it basically rescales the pixels to be between 0 and 1, and then it resizes the volume. So once you do the pre-processing, you will have this type of structure where you see the processed folders along with the raw ones, also for the validation. Once that's ready, you have the pre-processed data for the AMOS, CT-rate, and validation. You can start training. To do that, you can use this command. It's quite heavy, so I've split it into the most important arguments here. But before that, you can see one important thing to note here is the JSON path and the data route. The way this training script works is you have to pass in the JSON path and the data root for each data set. You can see here it's a list, so there's 2 items here, the AMOS one and then the CTRL one. There should be like a correspondence at the index level where the first index of the JSON path, this is the AMOS. First index of the data root, this is also AMOS data folder. So what the training script will do internally is add the full path to the file names in the JSON here. We'll do the same in this CTRL. So make sure that in your script, you can just copy this directly from the GitHub. If you do develop something yourself, then make sure that there is a correspondence here between the JSON and the data root. Okay, so what are the important training arguments in the previous script I showed? So you can disable and enable LoRa using this command, LoRa enable. If you want to freeze the backbone, there's an additional command called freeze backbone. This will override the LoRa. But if you have LoRa enable as false and freeze backbone as false, this will fully fine-tune the model. It's going to be quite heavy because it's around 4 billion parameters for Phi 3, and then if you go up in parameters, it's going to be even heavier. Task, this means all means MRG plus VQA, but you can change it to either MRG or VQA if you want to do some quick scripting to test your performance on either in isolation. It's going to be faster to train either one in isolation rather than both combined, but you can do you can change the task here. Number of epochs, that's the number of epochs. And then model, you can change the model that you want to use here. So currently we only support around 5 or 6 models. You can find those in the GitHub. So you would have to add additional model classes for models that are not already supported. So, but currently we support, like I said, 5 to 6 different models. You can change the path here from using the Hugging Face ID to the specific model. You have to change model type here also. This just lets the script which data class to use for instantiating the model, and then model max length. It's very important to keep this high because the global VQA, like we saw, has a bunch of different choices. So if you pass that as prompt, and this is low, like a lower value, I've even experimented with somewhere around 700. Just for reference, the visual tokens will take 256 tokens here. So the rest will be text tokens. But even if you use something like 700, like 500 would be for text, that's still too low for the global VQA. It's still going to cut off. So make sure that this value is high. It's going to be more expensive computationally, but you need it to work for the global VQA. And then the last thing is the VIT path, the M3T VIT path. So we can download it from their official Hugging Face repo. So you go here, M3T clip, and then you can see the VIT here. You have to download it from here. I can actually show you what training looks like once it's done. So I have the script loaded here. I can just run it. Let's make sure we're here. So just to see what it looks like. Hopefully this don't face any issues here. So it's gonna, if the model is not already downloaded, it's gonna download it first. Then it's gonna load it. You can see here then parameters. It's gonna show you the trainable parameters compared to all parameters as a percentage. So you can tell that this is using LoRa here. If you are freezing, the element will be lower, and then if you're full fine-tuning, all parameters will be trainable parameters also. The VIT here is always fine-tuned. But basically, yeah, so it should be training now. Okay, it is training. Okay, so this is what a successful train should look like. If you go back, after you train the model, it's going to be saved in the directory that you provide here. In the output directory here. I'm saving it in result-baseline, but it should be saved in whatever directory you provide here. Using the directory, you would need it to run inference. Basically, we have two separate inference scripts, one for report generation and one for VQA. The report generation inference script will already calculate the green for you. And then the visual question answering will just generate a CSV file. I'll show you what that looks like, and then you should submit that. But this will also generate a CSV file. I'll also show you what this looks like. But basically, what the script looks like is you pass in the path to the trained model. You pass in the JSON path for the pre-processed val JSON for the data route as well. Model max length prompt. So this is the number of additional tokens above that are not related to the prompt. So this is additional above the prompt. Prompt I just used. This is just a mapping. I have simple prompt here. This is just a mapping. When you type in simple prompt, I will transform this to just a very simple prompt that says, "Oh, you're an AI radiologist, and you should write a report for the CT scan." Something very simple. This you should keep, because this is dependent on the projector that you use. If you're using M3T, you should keep this as 256. So the inference code, so it's quite simple. The actual inference is just getting the images and then just using the generate function here and then decoding them back to text and then saving everything in a CSV file. But what's more important is this generate green score here. This function basically, as the name says, will generate green scores for you. There's a method in this in the class called compute region scores. It's important to notice here that what this script does is first looks for regions that are mentioned in both the ground truth and the generated report. These are called matching regions. For those, it just directly calculates the green. But otherwise, if the region is in the generated but not in the ground truth, it just compared to a normal finding. So just the region is normal, and then this can directly compared against it. But otherwise, you're going to get a 0 if the region is in the ground truth but not in your generated report. So I can actually quickly run inference actually to show you what that looks like. So assume that the model path for me is this. Assume that the JSON path is here. You can see if I run inference, I will load the model, and then I will just directly start inference. So this is the number of examples in the validation, and I will just run inference on them. And post inference, it will, like I said, it will generate a CSV. I can show you what that looks like. So we can see it will save the generated prediction. So split into different regions. So we can see here liver, spleen, pancreas, kidney, and all of these different regions. And then it will save the ground truth as well. Save the name of each example, and then this is the average screen. And then you can see green for each region here. So each region has its own green, and then the average is given here. And we also save a JSON that just JSON that looks like this. Basically, called summary to a JSON at the same path where the model lives. This JSON will just give you a summary for each region, summary of the green score for each region. For the VQA, it will just save the predictions. So, because we're not providing the answers for the VQA yet, you would have to submit your answers for us to evaluate those, because those are not computationally heavy, unlike the report generation. But basically, it will save, for each example, it will save multiple rows. So one global and then multiple locals. The locals here, the question ID, as you can see, there's a question ID column. This question ID corresponds to the root question. This question, so this is the root question, then this is a follow-up too. And then important thing to pay attention here is that the answer should be structured by using pipes to divide to separate the different answers. So there's two answers here. So this is okay, starting from question ID 1, this is the root question. The answer to the root question is yes. The answer to the follow-up question to the question that has ID 1 is this. And you can see the question here, which of the following features are present in deliver? These are the choices. You can see this is choice 1. Small volume, uneven surface, disproportionate lobes. So you can see here, small volume. So this is the structure that we expect that you submit. So answer to the root question, and then separated by like this pipe thing, and then answer to local questions, and it can be multiple. So if there's another question, it will just be like this. So the format for the global is just comma separated. Sorry. So the question choices, there's a multiple, and then the prediction should be comma separated. So one choice and then separated by a comma and then the other choice. For the local, like I said, it's separated by this pipe. So some failure cases, there's a bunch of these examples where the ground truth says that something is normal, but the generated reports doesn't. So this gets a low green score, 0.03. This gets all of the different regions incorrect, basically. So this says, and the deliver says that there's no obvious abnormal density, and then while this says that the deliver is enlarged. Spleen, this is it's enlarged, so this is the opposite, where the spleen is has a positive finding, while this one is normal dash negative. Spleen is not enlarged. So this is a failure case, and then for VQA, the model here gets the root question incorrect. So it doesn't matter what the answer to the second question is. So it says, is there evidence of cirrhosis in the liver? It says ground truth is yes, but this says no. So this chain will be 0. So you could just weight this more if you wanted the training, like I said. So I think I went through everything. If you have any questions, you can feel free to ask. We also provide the GitHub and the link to the GitHub where you can see the same steps that I just took. And if you have any questions, you can either raise an issue here or email me in the email I sent.
Okay, great work. Any questions from the audience? Okay, if not, thank you so much again for joining us, and also thank all the 3 great speakers. And so we will post the recording on the website in 24 hours. So feel free to check it, and also feel free to ask questions by post them on the forum or directly send an email to us. Okay, have a great day. Thank you so much.
Wait, I think someone has a question.
Yes, I have a
sorry.
question.
Oh, okay, go ahead.
It's a general question, not related to 3D task. So I wonder if we can submit more than one time per month, because it's mentioned that we only have one chance to submit for validation. However, it will be hard because we don't have also a way to evaluate our model, since we don't have regression samples and instance detection samples.
Okay, great point. Oh, okay. We will increase the Docker submission 3 times per month, but at the same time, you can submit the results on Coda bench. That one is you can submit 5, or remember it's 3, at least 3 times per day. It should be enough for the to
We
get the hidden validation
no?
performance.
I mean, the Docker file you are talking about, we can submit 3 times per month. Is that what are you saying?
Yes, yes, this is the first point. We will
Okay.
increase it to 3. Could you please update this on our channel website?
Okay, thanks so much.
And the second point is that you can directly submit the JSON file on Coda Bench to get the hidden validation performance.
Oh,
This
okay.
one for this option, you can do at least 3 times per day.
Okay, got it. But it's disabled to submit it, I think. There is development phase. It says it's over already. The due time is over.
Oh, really?
Thank you.
Okay. We will double check to fix this issue.
Thank
It should be okay. We'll double check to fix this.
Yes, thank you.
Okay. Thank you so much. Any other questions? Okay. If not, this is the end of today's webinar. Thanks again for joining us. Have a great day.
Thank you.
Thank you.